In the last section, we focused on how we could measure heat energy, Q, by using temperature changes and specific heats. In this section, we'll get into how we think about that heat as a part of the total energy available from a chemical system, which is often combined with another form of energy, the ability to do mechanical work, which we indicate with Q. We know that energy can change forms, which sometimes makes it difficult to keep track of. The two main ways we see energy at play in chemical systems are the heat energy, Q, and the work, W, which together we say make up the internal energy of the system, defined by the letter U, which is another way of saying the energy that's stored in the bonds. It's worth noting that we can't really quantify internal energy, only how it changes. If the energy stored in bonds does change, we indicate that with a delta U, and we know that energy will either become heat, given by the letter Q, or work, given by the letter W. Work often comes from gases. It happens when a system changes volumes. A great example is a combustion engine. Chemical energy from the gasoline is released as work, changing the volume of the combustion chamber and forcing the piston to move out. While you know conceptually how that works, it might not be apparent why pressure times volume, or change in volume, gives us work units, which are joules. The SI unit for pressure, the Pascal, has the values of newtons, which is a force unit, per meter squared, an area unit, pressure over area, or force over area is pressure. Volume, when indicated in meters cubed, combines with that pressure to give newton meters, the equivalent of the unit joule. We define work using the same convention that we use for heat. If heat is coming into the system, it is positive. Energy in gives a positive Q. If it's leaving the system, it's negative. A system that is doing work is going to be losing energy, so that work gets indicated with a negative value. On the other hand, sometimes the surroundings can change the system's internal energy. When your body makes ATP, it mechanically changes the available space around ADP, adenosine diphosphate, and a lone phosphate to create an ATP, adenosine triphosphate, that has higher energy. In these cases, the work is indicated as a positive because it increases the available internal energy in the chemical system. Work is often really difficult to measure. Chemists like to have systems where work is zero, which allows us to calculate the change in internal energy based only on Q. If the internal energy change is entirely from a change in heat, we describe it with the capital letter H, the enthalpy of the system, or we talk about those changes as delta H, the change in enthalpy. When the work is zero, delta H, the change in enthalpy, is equal to the delta U, the change in internal energy, but it's way easier to measure. Summarize once more. Delta U is the change in internal energy, the energy of chemical bonds. It can easily be converted to heat energy, Q, or work energy, W. Q is also known as the change in enthalpy of a system, a measure of that heat energy. Work is given for a system by negative pressure times the change in volume. The internal energy then can be fully given by the change in heat energy, enthalpy, indicated as delta H, and a change in pressure times volume. And it's nice for us when the volume doesn't change, because that means we can just measure the change in heat energy to get the total change in the energy of the chemical bonds. In these examples, the change in internal energy, delta U, the change in enthalpy, delta H, and the change in volume, delta V, will only depend on the initial and final states, not on the path it took to get there. That means we don't need to know the flow of Q at any moment in time, just where the reaction started and ended up. Values that are independent of path are called state functions, like elevation. It doesn't matter what path you took to get to the top, the elevation will always be the same. The opposite of a state function is a path-dependent function. For example, if we wanted to measure the distance it took to travel to a given elevation, it would matter how we actually traveled there. Because the change in enthalpy, delta H, is a state function, it's the same every time a reaction happens. Here we indicate the energy of a reaction between hydrogen and oxygen that happens in a fuel cell. The delta RH stands for the change in enthalpy of a reaction, or heat of reaction for short, a measure of how much energy is gained or lost from the chemical bonds. Remember that whenever we're using delta H, enthalpy, all the change in internal energy of chemical bonds is accounted for in that change of heat, since there's no work done by the system. Since the heat of this reaction is negative, it means that heat is being released from the system. These heats of reaction are tabulated for many reactions, which can make it easier to determine the energy of a reaction. But these need to be used very carefully. First, the energy applies to a reaction for exactly as many moles as written. So if we took the reaction listed on top and doubled the amount of moles participating, we'd have a change in enthalpy of reaction, or heat of reaction, that is twice as high. These reactions also are highly dependent on state. The reaction on tops gives us the amount of energy to react hydrogen and oxygen to make liquid water. But gaseous water is higher in energy. Since gaseous water maintains more of the internal energy, less energy is given off by the reaction, and the heat of reaction is a less negative number when we're talking about converting to gas. So the state really matters. Finally, it's difficult to measure the temperature of every component of the reaction independently, so these heats of reaction are given under standard ambient temperature and pressure conditions, 1 atmosphere and 25 degrees Celsius. We call these state conditions and indicate this with a degree sign after the H. There are ways to modify these values when conditions are not standard state, which you can talk about in Chem, you crazy glutton for punishment. In our previous lesson, we talked about the reaction coordinate diagrams in terms of Q for heat. It's more accurate to limit this to cases where work is not being done, where we could use delta H instead of Q. Delta H is negative in exothermic reactions and positive in endothermic reactions, just like Q. Heat of reaction is a universal term that applies to all reactions. These heats of reaction are cataloged for many simple reactions, even some in your text. Often these reactions are broken up by type to make it easier to find that information. Combustion reactions, whether they oxidize carbon or oxidize something else, are characterized by heats of reaction that are specifically known as a heat or enthalpy of combustion. A selection of these heats of combustion is included in your text as Table 9.2 under Section 9.3. We can also find in Appendix G heats of formation that are given for the formation of a substance from elements at standard states. In many cases, heats of formation describe reactions that don't actually happen directly, but they can still be found by combinations of other reactions because change in enthalpy is a state function. It doesn't matter what reactions it took to get to the final products. We'll do some examples where we use this in a little bit. Heats of formation require some assumption of a baseline energy to which we can compare. For elements, this energy is set to 0 and everything is compared to elemental forms. Most known compounds have negative heats of formation, which means they're formed from exothermic reactions, which also indicates that they're more stable than the elemental forms. That makes sense because if the world was filled with things that were less stable than the elements would separate over time. Since things are more stable, it makes sense that we actually see them in the world around us. If a heat of formation is given for a solution, the solution is considered to be 1 molar in concentration under standard conditions. So if you see a solution, assume the concentration is 1 molar for heat calculations. This heat of formation will now include the energy of dissolution, which is the energy it takes to dissolve that 1 molar solution. An extensive list of heats of reaction and heats of formation are included in the first column of Appendix G in your text. Pay no attention to the next 2 columns. Those are the cooler thermodynamic properties that predict whether a reaction will go and won't come up until next semester. Again, many of these reactions are not actually possible, but the heats of reaction can still be calculated from other reactions because they're state functions. It doesn't matter how we get to the products, just that we get there. This is essentially Hess's law, named for the German Germain Hess, who wrote it in 1840. Hess's law states that we can add and subtract heats of reaction as needed, even if they aren't the reaction we're looking to characterize, to give overall heats of reaction that are difficult to determine experimentally. For this to work, we need to make sure that the net reaction, the sum of all reactants and products, is actually equal to the reaction we want to characterize. The sign, and whether something is on the product or reactant side, and the state of every component are really important to check to make sure they're canceling the way that we need them to. For example, if we wanted to know the heat of formation of carbon monoxide, we'd be looking at the reaction carbon solid, the elemental state of carbon, plus oxygen gas, the elemental state of oxygen being combusted, and converting those to carbon monoxide. The problem is this reaction is always a side reaction in the more favorable combustion of carbon to carbon dioxide. As long as there's enough oxygen, that's going to happen instead. So that reaction can't be measured directly. We can, however, isolate and oxidize carbon monoxide to carbon dioxide and measure a heat of reaction for that. We can also react carbon with enough excess oxygen that all the carbon will become carbon dioxide, and we can measure a heat of enthalpy for that. When we subtract the combustion of carbon monoxide in yellow-orange from the combustion of carbon in blue, we get the equation in green and a heat of reaction of negative 111.0 kilojoules. If you look closely, the carbon monoxide on the reactant side is negative and the product has no molecules. But if we add carbon monoxide to both sides, it doesn't change the energy of the reaction. Since the exact same molecule is being added to both sides, it will give the same energy to both sides and still balance out. But now we've gone from a negative reactant to a positive product, which gives the same reaction we wanted in the first place. Thanks, Hess. Since heats of formation are also state functions, we can use these to find the heat of reactions as well. Each heat of formation is energy relative to elemental states. If heats of formation are used for both reactants and products, the elemental states end up canceling out to give just the energy of the reaction itself. This is just a simple way to use tabulated values for Hess's law calculations, since each time we see a substance we only need one heat of formation rather than to catalog every possible reaction it could go through. It's important to note that the heats of formation for the products give positive values, since these are the delta H values for the formation reactions as written, while the heats of formation for reactants are negative, as they represent the formation of things that are reacting away, which is the opposite of formation. Because these heats of formation are well documented for simple molecules, calculating heats of reaction are fairly simple. Try calculating the heat of reaction for the reaction shown, the formation of calcium oxide cement from the mineral calcite in limestone, using the heats of formation in your text, Appendix G. If we want to calculate the heat of reaction for this reaction, the first step is to find all the heats of formation from reactants and products. To one significant figure, this is what I found in Appendix G of our text. We will still take the sum of every product heat of formation and subtract the sum of every reactant heat of formation, which is the equivalent of the reaction occurring as written. As we perform the calculation, it's important to remember that if multiple moles of a product are present in the reaction, they need to be represented by taking the heat of formation multiple times, shown in this equation by multiplying each heat of formation by the coefficient, which just happens to be 1. The result is a positive 191.6 kilojoules for each mole basis of this reaction. That means the 191.6 kilojoules of energy need to be supplied by the environment for the calcium oxide to form. When limestone, basically calcium carbonate, is converted to cement, calcium oxide, the limestone needs to be heated, usually with fossil fuels releasing carbon dioxide. At the same time, carbon dioxide is necessarily a byproduct of this reaction, and even more is released from the reaction itself. So concrete production accounts for somewhere between 5 and 10% of global CO2 emissions. Ozinga and other industry leaders have done some work to reduce this by reintroducing carbon dioxide into the concrete mixture, the calcium oxide cement plus water and sand and aggregate. Such processes can actually capture and sequester a portion of the carbon dioxide that's produced in this reaction. For inorganic compounds, it's usually pretty straightforward, since we only encounter a limited number of inorganic compounds, and most of these values are tabulated directly. Organic molecules are much more difficult to tabulate this way, since there are so many possible combinations. Instead of trying to tabulate every single heat of formation for all possible molecules, we instead think about organic molecules' heats of formations based on the energy it takes to break individual bonds, called bond dissociation energies. For example, it takes quite a bit of energy to break apart a hydrogen atom, about 436 kilojoules. But if we do get it apart, that difference in energy must have come from the hydrogen-hydrogen bond, meaning it is the bond dissociation energy, associated or indicated with a D. We can do this with all sorts of molecules. Chlorine can be broken into two for less energy, so the D for chlorine is 243 kilojoules per mole. Breaking H and Cl apart into atoms, not ions, gives us the HCl bond dissociation energy of 432 kilojoules. These values are given in table 9.3 under section 9.4 of your text. We can also use these for a Hess's law type calculation. The change in bond energy between reactants and products can account for the differences in energy for the total reaction itself. The calculation has all the bonds broken as positive values. These are bond dissociations as written. The bonds formed are the opposite of bond dissociations, so they need to be subtracted instead. So for a reaction that happens between hydrogen and chlorine to form hydrochloric acid, we would just add the energies for the HH bond that was broken, the Cl-Cl bond that was broken, and subtract 2 times the energy of HCl for the 2 HCl molecules that were formed. Altogether, we get negative 185 kilojoules for this reaction, which would indicate that it's exothermic. If you compare this to the heat of formation that we could find in our text for HCl, which is listed as 92.307 kilojoules for 1 mole, or 184.6 kilojoules per 2 moles, which would be how we'd have to compare since this is a 2 mole of HCl formed, these are pretty close, but they won't be exactly right. Bond dissociation energies are always approximate values. We've talked about ionic bond strength being higher than most intermolecular forces. We can quantify this with the lattice energy, the amount of energy it takes to separate ions in a solid lattice completely into a gas phase. We do this using C, a constant related to the arrangement of ions, a crystal structure constant. And we give the lattice equation with C, the crystal structure constant, times Z plus, the charge of the cation, times Z minus, the charge of the anion, divided by the distance between the ions R0. However, the constant C can't be determined outside this equation, so we need lattice energies to start with before we can start to calculate any new lattice energies. There has to be another way of finding the lattice energy, so we can characterize that lattice. Max Born, a Nobel laureate famous for contributions to quantum mechanics, and Fritz Haber, a Nobel laureate famous for the Haber part of the Haber-Bosch process, together developed the concept of Born-Haber cycles to use known values of state functions to calculate lattice energies, kind of just like what we've been doing. Incidentally, Casimir Fajans, a Polish chemist who invented a way to measure nitrogen by titration, the Fajans titration, and discovered protactinium, also made this discovery independently, but he doesn't get the cycle named after him. The basic idea is this: starting from cesium solid and fluorine gas, a series of quantifiable heats of reaction can give us the energy required to form the gaseous ions. We can also combine them and measure the heat of formation for the solid ionic compound. Combining the heats of reaction for all these reactions together will give us a total of the reaction we're looking for and the heat of reaction for the solid to gas ion transition, the lattice energy. The first transition changes only the cesium solid to cesium gas. It's a phase change whose energy is given by the heat of sublimation. These are well known and easy to measure. The next transition converts cesium 0, the metallic cesium, to cesium plus 1. This is the ionization energy and is also easy to measure. Fluorine in its elemental state can be converted to atomic fluorine by dissociation, and that bond dissociation energy can be measured as well. And that's what we just did in the slide before this. From atomic fluorine, my new band name, the electron affinity gives the energy associated with ionization to fluoride. Going the other way, elemental cesium and fluoride can be reacted to form cesium fluoride, and the heat of formation gives the heat of reaction. When all these state functions are added together, the net result is that the equation that gives us the solid to ion gas transition, and the energy is the lattice energy. So this is a really cool application of combining those state functions that we've done before.